Mr. Rashid here, and welcome to another pre-calculus video. So today we are going to go over solving systems of equations using graphing, substitution, and elimination. And the specific examples I'm looking at here today are with two variables and with two equations. So before we get into the methods, let's talk a little bit about some vocabulary and definitions. So a system of equations is a set of two or more equations, and these equations are connected somehow to an actual problem where we have some unknowns. We'd have two unknowns and we have two equations. The solution for these systems of equations is written as an ordered pair if you've got two equations and two unknowns, or an ordered triplet if you've got three unknowns, and ordered tuple if you've got more than that. And sometimes it's also known as an n-tuple. So in this case there are 6 of them, so we could write this here is a 6-tuple. Okay, before we look at the methods then, we can solve systems of equations by graphing, which is the first method we'll look at. And these are two graphs that we can see of two different systems of equations. Now, each part of the system is a line. So there's the first part in the 2 by 2 system. The first part is a line, the second part is a line. So the solution to this system is where those lines intersect. It's right there. So in this case, the solution is 3, -2. Or in this second problem here, it's at 4, -4. Now, any other points here are not solutions of the system because they don't fall onto both of the lines. Now, if you have the graph, you could see it right away, but many times we don't have the graph, so we have to do things algebraically. And how you solve or look for whether the ordered pair here is a solution is you plug it in to both equations and make sure that it checks out. So if I plug in 3 and 4 here, 3 plus 4 is 7, that checks out. So let me put it in the second equation now. So I get 4 equals -8 times 3 minus 3. This is -24 minus 3. That is -27, so no, those are not equal. So 3, 4 is not a solution to that system. So that's an example how you check it out. It has to work in both of those equations. Now let's talk about something else here with systems of equations. So the two problems up here, they worked out perfectly. Those lines had different slopes and then they intersected at a point, but we can have a situation. So this is the first thing that could happen is both of the lines intersect and we've got one solution. This is for two equations, two variables. The other thing that could happen is both of the lines are parallel and we've got no solution. They just never intersect to give us that intersection point. And then the last possible case is that we have one line and another line, and they're coinciding as we saw in the last chapter, and that means they're sitting on top of each other, so there's infinitely many places where they're the same. So that's infinitely many solutions. So those are the 3 possibilities here on the coordinate plane. So let's look at now the 3 methods to solve systems of equations. The first one is by graphing. Now, graphing is the best method of solving when you're just given the line or the curve on a graph and you're not given the actual equation, so you're stuck with having to use graphing because that's all you've got to work with, and you can't do the algebra, you don't have the equation, so that may be a situation where that graphing would be the best way to do it. Then another place where you could use graphing is in nonlinear systems, where you might sketch a quick graph to figure out how many solutions there are to the system before actually doing the work. So that's another place where it's good to use some graphing. Other than that, graphing is generally very slow. It takes a lot of time, and it's also can result in inaccurate answers if you're not doing things precisely. Even when you do things perfectly, sometimes the numbers are just not able to be read from the graph that you have. So your graph is not precise enough. So let's see an example that everything works out well. So y equals 2x plus 3. So my y-intercept is at 3, and then I have a slope of 2. So one thing I do with graphing, especially when I don't have a ruler handy, is I'm going to just put dots on every possible point here so that I can clearly see my intersection. So there, 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 there. Okay, and then let's do the next one. Y equals half x minus 3. So my y-intercept is there, and then my slope is 1, rise of 1, and run of 2. So there, there. Okay, I got lucky. I found my intersection point. I'll just keep going for a little bit, but this is my intersection point right there. So that is -4, -4. And so that's something I solved using graphing, right? So I was able to get that done with graphing, and things worked out perfectly. But there are lots of cases where you're just not going to be able to solve the system by graphing, like in this one here, 2.538, unless you had access to a calculator like Desmos, you wouldn't be able to graph that precise enough on your paper with just a pencil and your ruler. So that's why we need better methods. So the second method is substitution, and substitution is the best method when one or more variables are already isolated. So here's an example where y equals 3x, we got the y alone by itself. So now I can take that 3x and substitute it in place of the y and rewrite this whole thing as x plus 3x equals 12, which is 4x equals 12, or x equals 3, and then now I take the 3 and plug it back in, maybe do the first one or the second, it doesn't really matter, and I get that y is equal to 9. So now I can write my solution for this system here as 3, 9. And so so that is essentially the method of substitution. If you're asked to use substitution and one of the variables is not isolated, it just makes things more difficult. So there are other methods available. And elimination is the third method. And this is where both equations are written in standard form. And you would line things up like this. So here's one case where 2x plus y equals 3 and 3x plus y equals 7. So you'd line up the x's like that. And you want to eliminate by adding the two equations. So before we could do anything in this case, we would have to multiply maybe the second equation by -1. And then rewrite the whole system as 2x plus y equals 3, -3x plus -y equals -7. And now I could add this whole thing, and then if I added here, my y's would go away. So in another example here, so if I added negative 2x plus 2x, that's 0. 4y plus 6y is 10y. 10 plus 20 is 30. And then dividing, you get y is equal to 3. And then I plug that back into one of these equations to get my x value. So that's how things look with elimination. Now, things can get a little bit more difficult when you have, it's not so clear what you're going to do here. So we have this example where if I line things up, 4 plus negative 8, things don't cancel, or 2 plus 4, things don't cancel. So I'd look at my 4 and my 8 here, my 4 there and my 8, and find the least common multiple. And the least common multiple here is 8. So that's an example where now I know that I'm shooting for getting 8 in front of that x. So what do? I would need to multiply that 4, or everything in the top equation here, by 2. And then let's rewrite this as 8x plus, everything's getting distributed here, 4y equals 16, and nothing happened to the second. I didn't do anything there. 4y equals negative 16. And then now I would add these two, and that would eliminate. So you don't have to do it with the x's. You could have done it with the y's, but that's an example how you would deal with a case where it's not so straightforward. So in the last bit here, I'm going to look at specific situations and how I can turn them into systems. So a drawer contains 24 spoons and forks. So I could maybe say spoons are my x, my unknown, the number of spoons are my x, the number of forks is y. And so I could write 24 equals x plus y. Then there are 3 times as many spoons as forks. So if there are 3 spoons, then there's only 1 fork. So we could say that 3 times my forks, which is y here, is equal to x. So if I had 1 fork, then there are 3 spoons. And so that is my system of equations, and I would write it like this from that situation. So a parking lot has a total of 60 cars and trucks. So let's say that's x and that's y. 60 equals x plus y. Then the ratio of cars to trucks. So the ratio is, that's another word for division. So ratio of cars to, let's use my x and y here. Ratio of cars to trucks is equal to, and this colon 7 to 3 we could say is a division as well. So it's 7 over 3. If I cross multiply here, I get 3x equals 7y. So that is another example of a system of equations. Let's look at 1 or 2 more here. So in this case, there are 13 animals in the barn, and some are chickens and some are pigs. So let's use different variables here. Maybe I'll call the chickens the C and the pigs P. So P plus C equals 13. So that's P, that stands for the number of chickens and the number of pigs. There are 40 legs in all. So there's, chickens have 2 feet. So 2 times the chickens, number of chickens, plus 4, because pigs have 4 feet, 4 times the number of pigs is equal to 40. And so that then is my system of equations for that situation. So that's it, and I'll see you in the next video. Bye.